Aldol is a wonder reaction, right? In fact, we're aldolizing all the time in biochemistry. It's a huge biochemical reaction, as you can probably imagine with all those carbonyls and enolates floating around. We aldol, but it's not all goodness and light. So what we're going to try and cover in this mini lecture is really section 18.8 and a little bit of 18.9. The start to looking at the twists and turns of the aldol. And one of the biggest twists and turns is, it's a real problem, and that is when you're not real careful choosing your aldol partners, it can get really ugly. So, let's say I want to take acetophenone, that's molecule A, and react it with acetone, that's molecule B. I throw them together into my beaker, add my base, and let her rip. Hey, that's going to be a problem, because I am going to get this nucleophile, and I'm going to get this nucleophile. And this nucleophile can react with itself, or it can react with acetone. And this nucleophile can react with itself, or acetophenone. So I have a total possibility of 4 products, and that's not even including the dehydrated products. So I could get this, I could get this, I could get this, and I could get this. And you know what? I'm missing a methyl group there, and get it there. My TLC plate is going to look like this. It's just going to be awful. It's what we call a tire skid mark on your TLC. You got garbage. So when you want to make aldols between 2 different carbonyl compounds, which you want to do quite a bit actually, you have to be careful. There are ways around this. For example, we can make sure, it depends on what you're trying to make, but you can make sure that one of the 2 carbonyl species doesn't have an alpha hydrogen. No alpha hydrogen, then you can't generate an enolate, and therefore that means the only thing that's going to happen is this enolate is going to form, and while it could react with itself, there are ways to make sure it only reacts with the other carbonyl partner. So that simplifies things quite a bit. Another thing you can do is just make sure that when you do try to do a mixed aldol between 2 species, make sure you have figured out a way to make the enolate of the one you want to enolize, make it stoichiometrically first, let it just be sitting there, and then you can add the other. So let me explain. Here is my target. That means I want to, that's not the 7-membered ring. Those dreadful 7-membered rings, so hard to draw. I want to make this enolate, and I want to react it with this aldehyde. So if I can just figure out a way to make this first, and then make sure I add this to that enolate, I shouldn't have any trouble. Well, it's not impossible. For example, I just make sure that I have my cycloheptanone in my beaker and carefully add my base so that as the enolate is formed, it's just sitting there and not reacting with anything. And then I can add that enolate to this aldehyde and control the reaction that way. But as you can see, if you start to think about it, you have to think about order of addition. Should I add the base to my ketone, or should I add my ketone to my base? Should I add the enolate to the aldehyde, or should I add the aldehyde to the enolate? These are all good questions, and if you're ever going to try and carry out an aldol in the lab, the order of addition is really going to matter. Other interesting twists to the aldol? Well, what's the product of this reaction? I see an aldehyde, but not another carbonyl. Well, you're right, there's no other carbonyl, but you certainly know that the NO2 group is a very good electron withdrawing group, and so it is just as easy to deprotonate a nitroalkane as it is to deprotonate the alpha hydrogen of an aldehyde or ketone. So in other words, this guy right here is going to be giving me my nucleophile, my enolate partner, right there, and that will react right there to give me the aldol. There's my OH. Here is my NO2. Here is the new bond I just made. Here's the rest of my molecule. It was a 1, 2, 3, 4, 1, 2, 3, 4 carbon long molecule. And given the conditions, it certainly looks to me like we're going to lose water to end up with this guy. 1, 2, 3, 4. That should be my product. And is it an aldol? Yeah, it's an aldol. All of these things where an enolate type molecule reacts with a carbonyl, that's an aldol. How about this twist? Well, okay, I can see that there's no alpha hydrogens here, but remember what we're talking about now is an electrophile at that beta carbon. Remember the resonance contributor that shows me this guy is an electrophile. So we're talking Michael addition here. And what's important to know is that an enolate is a soft nucleophile that very happily reacts 1,4 with a conjugated system. So first step in the mechanism, after deprotonation of the alpha hydrogen to give me my enolate, I've got my CH2, my CH, my double bond to my oxygen, and my hydrogen. So there's my intermediate, my enolate intermediate, and that will then reach right out and grab a proton from my solvent to give me my final product, which is the 1,4 addition product. So I've got a CH2 and a CH2. Oh, I've got a CH2, CH2, CH3. Be careful here. Let's just color code this. The enal is this bit, and the original enolate is this bit. The new bond that was formed was right there. And here's another bell and whistle for you. 1, 2, 3, 4, 5. That's bells and whistles for a Michael reaction. And to be perfectly honest with you, a Michael reaction really does legitimately mean addition of an enolate. So aldols give you that bell and whistle of a 1,3 alcohol and carbonyl. A Michael gives you the 0.15 relationship of the two carbonyls. Whew, that's a lot. That's a lot of interesting twists. Just think mechanism and you will be A-OK.